Hello and welcome back to the series of lectures on high performance computing. So far we have been looking at computer architecture, and today we'll go a little bit further in trying to figure out what are the typical issues with storage/memory with computer architecture. Before we go ahead, let us revise a few concepts. We had discussed what was the von Neumann architecture, where you had a central processing unit which has the control unit, has the arithmetic logic unit, which interfaces with the memory unit where both the instructions for the program and also the operands or the data for the program reside. You typically have a physical input device and then you have some sort of an appropriate output device. We had also discussed that the typical program flow takes place in the following format. This is what the execution cycle looks like. You have an instruction fetch, which basically gets the instruction from program storage, which is stored in the memory. A program typically contains several instructions of the order of thousands, if not millions. Each instruction is then decoded and it's figured out what needs to be done with this instruction. And then you have an operand fetch, followed by the execution of the instruction, and then you store the result until you go ahead to the next instruction. And this cycle goes on until all the instructions are exhausted. Now, obviously, we have to store thousands of instructions in memory, which take up space. The other thing that we need to store is the data on which these instructions work, or the operands. Now, both require space, and we will see how this memory is sort of organized in today's class. So, we will deal mainly with memory issues and access issues of this memory. Remember that when we say memory, here it essentially means the list of data members of the operands, which could be anything, could be a set of numbers, could be a set of characters, could be information that has been supplied by the user. It also consists of things which the program calculates during the execution of the program. And finally, the desired output which is culled from these calculations. The program itself, as we discussed earlier, is first written in some sort of a higher level language, which is then via the means of a compiler reduced to a set of machine instructions which are then stored in a place. And that's the set of instructions that those are going to be executed. So now let us discuss how is the memory in a computer organized. Is it all uniform? Is it different? Are there different classes in memory? Are there different hierarchies of memory? So this is what we typically look at. We have realized that we have semiconductor technology, which is essentially all the logic circuits which are doing your calculation, which are in your microprocessor. The same microprocessor also contains what is called as registers, which store bits of information. This bits of information includes instructions, includes the data members as well. So there's an instruction register and then there's a data register. Now this register memory is the closest to the logic circuits and hence the fastest in terms of access. The next level of memory is what is called as cache. Now this is some sort of a temporary storage. Now it is quite obvious that if we were to rely only on CPU registers for storage of instructions and storage of the operands, we would be quite limited by the size of the program that we are about to be able to execute, or the size of the data on which the program is going to be executed. Because CPU registers are very, very expensive to construct, and obviously they also have a finite size. Now, you can have another set of temporary storage areas which is called as cache. Nowadays cache can be of multiple levels, level 1, 2, 3, so on and so forth, which is still on the microprocessor but a little bit further away from the logic circuits which are actually doing the calculations. By virtue of being slightly away, what essentially happens is that you're able to store larger amounts of data. So level 1 caches will be usually some multiples of the CPU register in size. Level 2, which is even further away from level 1 caches, will be larger. One of the artifacts of getting closer and closer to the logic circuits where the actual calculations are being done is the fact that memory will become more expensive. By expensive, I mean that if you want to create a few kilobytes of storage close to the logic circuits, the manufacturing costs will be prohibitively high. But when you take it away from the real estate, when you take it further away, it will become cheaper. It's much easier to, fit in larger amounts of memory, and hence it's cheaper to construct from an engineering perspective. But there is a downside to it. The downside being that obviously if I'm very close to the CPU, if I'm very close to the logic circuits where all the calculation is taking place, obviously I'm going to be much faster. Data is going to be accessed faster, instructions are going to be accessed faster. But they're also costly. But the further away that I am, data is going to be slower because I need more time to get to that data, but it's going to be a little bit cheaper. You can go one level outside the microprocessor itself. As I said, the top triangles over here, the CPU register, the cache, etc., are directly on the microprocessor itself. Whereas from the level RAM onwards, RAM stands for random access memory, where you could have the physical random access memory. And then there's another concept called virtual memory, which we will address very soon. These are memory locations which are no longer on the same microprocessor. They are in fact connected separately using a motherboard. So to access this memory, data needs to travel from the microprocessor onto the motherboard and then onto the RAM, and then vice versa when data needs to be pulled out. Obviously, this makes things much slower, but it also improves the quantity of memory that we're able to store. Here we can get several orders of magnitude of memory that can be stored in random access memory. For example, typically today in the most modern processors, the size of cache is of the order of few kilobytes. CPU registers even lesser than that. Whereas typically we know the random access memory in a desktop machine or a laptop machine is of the order of few gigabytes at least. So we can store larger and larger amounts of data in random access memory. Now, if we run out of temporary storage areas, we can move also into permanent storage areas, which is basically read-only memories or BIOSes, but these are very special cases of memory where very, very small system-specific programs are stored. But then we have removable drives like floppy disks, USB drives, so on and so forth. We have network, internet, and cloud storage, and we also have the ubiquitous hard drive or the solid-state drives. Now, these permanent storage areas provide much larger storage capacity, but obviously they are much slower. Now, what we really need to understand by the term faster or slower memory. We must realize that the time in the CPU world is measured by clock cycles, and typically we figure out how many clock cycles does it take to access some amount of memory. In the CPU registers, data is usually accessed within a clock cycle, or I shouldn't say within a clock cycle because typically bare minimum it has to take one clock cycle. So a couple of clock cycles and you get data from the local register. From level 1 cache, it's a few clock cycles, same with about level 2. Level 2 will be a little bit slower compared to level 1. But the moment you start going out of this cache, which is essentially you're going outside the package of the microprocessor, onto the motherboard and then onto the physical RAM, we are now talking about few hundreds of cycles. If the worst comes to worst, you have to store data on the storage devices. That means if you need to get your data read from storage devices, it can go up to a few thousands of cycles. That means for a few thousand cycles, the CPU is doing nothing. Let's go back to the execution cycle. Let's imagine that you request some operand, and this operand now does not exist next to your CPU register, does not exist in the cache, but actually exists in the main physical RAM. So it will take about 100 clock cycles for the computer to go and fetch the operands. During that 100 clock cycles, you'll have to wait because execution cannot begin, and hopefully there is some other sorts of parallel pipelining which is going on, which we had discussed in the previous class, where those empty clock cycles could be used. But for that particular instruction, you would have to wait those 100 cycles, 100 odd cycles before execution can begin. And this is sort of fairly inefficient. So you can now see that this is how the CPU memory is organized. So you have CPU registers over here, then the second level cache, then memory, and then finally the disk. And you can also see that these are what are called as bus lines, or the circuits which actually transmit data back and forth between the data storage locations. And you can see the amount of data that is pumped from CPU registers to caches is of the order of bytes. From cache to memory is of the order of 4 times, about 32 bytes. From memory to disk, it's about 4 kilobytes. So you can notice that the data width is actually changing. Now the question is, why does this happen? The analogy I can give you is, let's say that you are a supply chain company and you want to distribute a certain product in a city. Registers can be thought about as the absolute last mile store houses, where some amount of product is stored, which can be delivered to whoever they want at the moment's instance. Now, in a city, there would be multiple caches or multiple larger mid-level warehouses where more amount of the product is stored. The reason why companies would organize things like this is obviously in the city, in the innermost city, real estate would be very expensive. Slightly outside in the city, maybe the real estate is not as expensive, so you could afford slightly larger warehouse. And even further outside the city, you could afford extremely large warehouses. Now let's say that you want to order one batch of the product. It would be very inefficient to just go get one batch all the way from the big warehouse all the way into the smallest warehouse inside the city. So you would do this in stages. You would have some sort of a small truck which delivers data from the medium-sized warehouse to the smallest warehouse, some extremely large truck to go from the large warehouse to the medium warehouse, and so on and so forth. We also notice one more thing, as what are the transfer rates between various levels of cache. We notice that data is transferred the fastest between CPU and the cache, and typically this is of the order of a few gigabytes per second. Data is also transferred reasonably fast between cache and the main memory, though it is usually at a fraction of the rate of CPU to cache. From the memory to the disk, however, that is typically extremely slow. Now, these figures of about 187 Mbps, which is a serial ATA standard from a few years ago. These numbers keep improving and keep changing over the years, but what is important to remember is the fact that these ratios are more or less maintained. In the sense that if the memory to main disk speed goes up to say maybe 1 Gbps, then the cache to main memory speed will go up proportionally by the same factor. CPU cache memory will also typically go up by the same factor. So that's typically what the engineering standards are. Now, this also brings to the question about the finite sizes of memory. Now, we all know that memory is of a finite size at each level. CPU registers are of a few kilobytes, cache is a few more kilobytes, memory is few megabytes to few gigabytes. Disk is nowadays in local machines can go up to a terabyte or so. At every stage we realize the amount of data that can be stored is finite. Now, how do I design a program where I am not aware of the size of the memory in the first place? For example, I could write the same program on a machine which has an upper limit disk of maybe just 10 gigabytes, an upper limit of main memory of maybe just 1 gigabyte. But the same program might have to work on a machine which has 1 terabyte of main memory and probably few petabytes of disk. That's quite possible too. So how do I write a program which is able to access all this memory without a priori knowing what is the size of the memory of the machine on which it's going to run? How do I deal with the addressing of this memory? Remember, finally, when we store data, we store them at specific memory addresses, and we need a way to figure out where which data lies. This is where the concept of virtual memory comes in. So virtual memory is some sort of a mapping. Virtual memory, essentially what it does is that for every program that is run, you have a certain address space, where the address in the physical memory, or rather the address in the virtual memory, is mapped to the physical memory. Now, this physical memory, something like a RAM, can host several programs at the same time. Remember, we had talked about earlier that how you could run multiple programs on the same machine. You could have a web browser running, you could have your scientific computation running, you could have a spreadsheet running, so on and so forth. So each of these programs has its own memory that needs to be allocated on the physical system. But for my specific program of scientific computing, I have one long list of items which are addressed in this virtual memory. But where is it stored? Now this is managed by the operating system in a very smart way called virtual memory and paging. So what happens is that this entire virtual memory, where your data is actually indexed, is mapped onto different parts of the physical memory. Some part of it might go into the random access memory or the RAM chips. Some, if the virtual memory is large enough, might go to disk. Some might be in the cache. It all depends on how big or how much memory your program demands and how the memory is organized. Now, the way the organization also takes place is in the form of pages. For example, it's not just one bit by one bit is the memory copied. You take a whole chunk of memory, a whole page of memory, and you store it on the appropriate part. And when a certain data member is required, that page of memory is moved from the slowest part or the highest level of memory to the one which is to the lowest memory, page by page. So one page will be moved. Let's say you have a page which is stored on the disk and you're now requesting a data member from that particular page. That whole page will now be moved to the physical memory first. Then another page from there, a smaller page from there will be moved to the cache. A much smaller page from there will be moved to the register, to the actual data that you need. Obviously, since space is limited in each and every location, if I am moving a page of memory from the disk to the RAM, some page has to be discarded, or rather some page has to be pushed back into the disk. So another page will be sort of moved to the disk, making access to that page slow. The least accessed page typically is then now sort of moved to the disk, and now but this is in the hands of the operating system on how it controls which page is moved to the disk. Now, if you have a program which constantly requests data in a sort of a random manner without any particular pattern, it's quite possible that most of the time you're asking data from the disk. Then what happens is that the page is pulled from the disk, put into the physical memory. When this is done, a page from the physical memory has to be flushed out. So that's flushed out to the disk. Now, if another random data is requested, that means another page has to come in, that means another page has to go out from here. And this process can continue endlessly, where you can keep swapping pages of memory back and forth between the RAM and disk, slowing things incredibly down. Because if you take a page of data and you're just using one member of the data rather than all of it, the effort to take that whole page of data is still the same. So it makes it incredibly hard on the computer. And this is, sometimes you would notice that your computer slows down tremendously when a particular program is running. That essentially means that there's a lot of back and forth going on between the RAM and the disk, or between different levels of memory. And that's essentially the concept of page thrashing, where one page goes out of memory, comes back in, goes out of memory, comes back in, so on and so forth. And this process happens quite vigorously. So ideally, you want to access data in a more uniform or in a more contiguous manner. Now, one would ask, then why would I even go through this entire pain of having things in a virtual memory, putting it in pages, accessing it in this weird manner where parts of the pages are in physical memory and parts of the pages are in disk? The entire idea is that then I'm able to write programs which are able to access much, much larger memories, right? Otherwise, I will need to know what the size of the memory, physical memory is, and be able to program only to that limit. Whereas now, once I have it virtualized, I can now take it to any sort of machine and allocate memory as and when I want. So this makes life a little bit easier for the programmer, while it brings in other challenges. So we now have to look at something called as the memory hierarchy terminology. So we realize that there are different levels of memory. Whenever I request a data, and if it appears in the uppermost level or the level closest to the CPU in the block X, it's called a hit. Now, obviously all requests will not be a hit. There is a certain hit rate. The fraction of memory which accesses are found in the uppermost level. Now, if you do not get a hit, you have a miss. So this is the amount of data that needs to be retrieved from a block which is in the lower level. So the miss rate is essentially 1 minus the hit rate. The hit time is the time it takes to access the upper level, which consists of time to determine. You need to know whether the data exists in the upper level or not. So you need to make that decision. So the time it takes to make that decision plus the access time. Now, in case there is no hit, there is a miss penalty. So the time it will take to replace the whole block in the upper level, bring in a block from the lower level, and then access that. And typically we notice that hit time is much lower in terms of miss penalty. Remember again, all these times in this level are measured in terms of clock cycles. Now, if you look at memory hierarchy, this is typically the hierarchy that you have. The speed over here is about a nanosecond or 1 clock cycle. The speed to access to L1 cache is about 2 nanoseconds, L2 cache is about 6 nanoseconds. Main memory is about 100 nanoseconds, as I said, about 100x of what it is for the registers. And secondary memory like the disk can go up to 10 million nanoseconds. So it's very, very expensive in terms of time to get data from the secondary memory. But when you look at it, the actual cost of how much it's data that can be stored, data can be stored at a real fraction of cost at the secondary memory. So it's always important that you have to write small programs, efficient programs, but sometimes you cannot get away with it. For example, AI and machine learning workloads typically have extremely large data sets, and you cannot imagine to store all of them within L1, L2 cache or main memory. Sometimes you have to go to secondary memory. The only way to make the computations efficient is to see to that once the data comes down to the lower level of caches, that you are more and more efficient and that you use that data repeatedly so that you get the most bang for your buck. Thank you.